This lesson will act as a sort of recap to the previous lesson concerning the unit circle. In the previous lesson, when we had talked about and established the concepts and values within the unit circle, we also spent quite a bit of time talking about the patterns within the unit circle. On this page, we have some of those patterns outlined. The patterns we focus on here relate to the patterns for the radian measures of the values within the unit circle, as well as the x and y coordinates there. For the radian measures, note that every radian measure is either a whole number amount of radians, for example pi or 2 pi or 0, or it is a non-reducible fraction with denominators 2, 3, 4, or 6. All the angle measures that we saw were all values that we could write in radians as pi over 6, pi over 3, pi over 4, pi over 2, or any multiples of those. For example, we saw pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. And all of those were the same distance away from the x-axis, as well as the y-axis. That means that any of those angle measures that had pi over 6 in them had very similar x and y coordinates, which is why it's really good to recognize those connections. For the radian measures as well, note that the fractions of pi get larger as you rotate counterclockwise from the standard position, which means that the fractions of pi with larger denominators are closer to the x-axis. For example, in the diagram on the right, pi over 6 has a larger denominator and therefore it is closer to the x-axis compared to, say, pi over 3, which has a smaller denominator and is closer to the y-axis. So that itself can help. Note that this really only directly relates to angle measures of pi thirds, fourths, and pi sixths. This doesn't necessarily correlate to all angle measures of pi over some denominator. If you look at the x and y coordinates, whether the x coordinates or the cosine value for each measure, we see that the values decrease as you approach pi halves, or the y-axis. The x values go from 1 to root 3 over 2, to root 2 over 2, to 1 over 2, and eventually to 0. As demonstrated before, if you consider 1 over 2 as square root of 1 divided by 2, if you consider 1 as square root of 4 divided by 2, and if you consider 0 as square root of 0 divided by 2, then this pattern is completely valid all the way through. We see the x coordinates from the x-axis go from root 4 over 2 to root 3 over 2 to root 2 over 2 to root 1 over 2 to root 0 over 2. The opposite applies to the y coordinates, where the y coordinates increase as you get closer to the y-axis by using the same values. Now, one of the main concepts there was what I was talking about in terms of pi over 6 and 5 pi over 6 and 7 pi over 6, all having the same x and y coordinates, but with different positive and negative values depending on their position. That brings us to our last bullet here. For a non-quadrantal angle measure, theta. Remember, quadrantal angle measures are those such as 0, pi halves, pi, those that sit on the axes. We say that the reference angle for theta, usually denoted as another Greek letter alpha, is the acute angle made between the terminal side of theta and the x-axis. Meaning, if you consider this to be in quadrant 2, for example, the flipped version of this over the y-axis, the reference angle is always the angle measure from the closest x-axis. Now, in quadrant 1, that means each angle measure is its own reference. For example, pi 6, the distance to the x-axis, is also pi over 6. For all the other angle measures, that is also true. However, for the angle measures in quadrant 2, for example, from 5 pi 6 down to pi, the difference there, if you subtract pi minus 5 pi over 6, is just pi over 6. Or, say one of the angle measures we had in quadrant 3, 5 pi over 4, the closest x-axis is also the negative x-axis, which is also represented as pi, and the distance to that is pi over 4. In quadrant 4, one of the angle measures we had was 5 pi over 3. 5 pi over 3 is closest to the positive x-axis, which you can represent as 2 pi. And if you subtract 5 pi over 3 from that, you will just get pi over 3. Essentially, each of these angle measures in radians, for example, 5 pi over 6, its reference angle is just pi over 6. 5 pi over 4, its reference is pi over 4. 5 pi over 3, its reference is just pi over 3. That is what a reference angle is known as. You can also do these in degrees. However, they're less simple to do. Whereas in radians, you're typically just taking off the number in the numerator. For example, 210 degrees, that is closer to the x-axis at 180 degrees, closer to 180 than it is to 0 or 360. And the difference to that is 30 degrees. So the reference angle to 210 would be 30 degrees. That's a little bit less intuitive than looking at a fraction and taking out the value in the numerator. The reason that that is important is because of what we call the reference angle theorem. The reference angle theorem states that if you suppose alpha is the reference angle for theta, for example, pi fourths would be alpha in this case as a reference angle for 5 pi fourths or 3 pi fourths or 7 pi fourths. Then cosine of the angle measure you're working with, say 7 pi fourths, is either going to be positive or negative version of cosine of the reference angle. And that is also true for sine. What that means, as an example, is that if you are, say, working with cosine of 3 pi over 4, then this is either going to be positive or negative cosine of the reference angle of 3 pi fourths. And the reference angle of 3 pi over 4 is simply pi over 4. Plus or minus in this case, however, is determined based on what quadrant you are located in. With cosine of 3 pi fourths, it's either going to be positive or negative cosine of pi fourths, and the positive or negative will determine based on the quadrant. In this case, 3 pi over 4 is in quadrant 2, and in quadrant 2, cosine, or the x-coordinate, is negative. So, because we're in quadrant 2, this is going to be negative cosine of pi over 4, not positive. That is the reference angle theorem, and we can use that to try to calculate a lot of angle measures here. The general strategy with the reference angle theorem is that you first determine what quadrant your angle measure is in, which will tell you positive or negative. Then you determine the reference angle for the angle measure you have. Once you know that, then you evaluate your trig function at the reference angle that you have, aka You evaluate your trig function for the angle measure in quadrant 1. As stated in the previous lesson, most things are going to boil down to your understanding of quadrant 1. If you understand how quadrant 1 works, then you'll understand how everything works.